Hello everyone and welcome to the Electrification Enthusiast channel. Today we are going to learn how to make custom components using the Simscape language. I don't know if you even knew that was possible, but you can build your own blocks that do whatever you want, and you can do it using something called the Simscape language. And so we're going to go through how you do this. We're going to do it with the example of a battery because everyone loves batteries these days. We're going to build a basic behavioral battery that lets you do a couple things. Specify its nominal voltage, specify its amp hour rating, specify terminal resistance, and then this is the part that's really important and translates to a lot of different places, but you're going to specify the mapping of voltage to SOC. You're going to create this nonlinear relationship between SOC and voltage, and the ability to do that in the Simscape language means that you can make any nonlinear relationship you want between any two variables, voltage and current, voltage and heat, current and heat, temperature or heat flow. Gives you complete control because no one's going to make every permutation of any block you need. This gives you the ability to add them when you need to, and it's really not that hard. So here you can see as I discharge this battery, we see this nonlinear voltage. We'll get a quick dip at the beginning and then a bit more linear behavior and then another big dip once we get to lower SOCs. Now, we would usually use the more detailed data vector and smooth this out. This is very choppy because we're just using a simplistic vector as an example, but this is going to teach you how to build any Simscape component you might need for any analysis task you might have. So let's get into this. We're going to break this up into individual steps because there's a lot of components, but a lot of it you don't have to have memorized. There's a lot of pieces where you can cut and paste if you know where to get the right data. So we're going to start by building this really basic voltage source. So we're just going to recreate the Simscape voltage source, something that gives out 10 volts. Then we're going to go and we're going to add terminal resistance. So we're drawing 10 amps at a 0.02 ohms, so we get this 0.2 volt drop. So we see that there. We're going to add the SOC in that nonlinear behavior. So this is the really important part from an analysis perspective. And it's pretty easy once we have the framework set up. And so we can add this nonlinear mapping that looks however we want because we just put in data points. And after that, we're going to take this block that does not look nice and we're going to make it look nice because no matter how much effort you put on the inside of your block, the vast majority of people care more about the outside because that's just how, as humans, a lot of people act. Just take the time, make things look nice, and people will be much more impressed by your work. So let's close this out and actually get started building this block from scratch. Alright, so we're going to rename this to example battery.ssc. And that is because a .ssc is a Simscape language component. And from the very beginning, I don't recommend memorizing a lot about the Simscape language. I recommend understanding it and using templates to put in the behavior you need. So the first thing we wanted to do, we wanted to build a basic voltage source, and we want to, let's open up the model that I had, and let's steal most of it. We're just going to get rid of the battery. So I have this basic circuit that draws 10 amps and measures the voltage, and I want to build my own battery block that goes here. Now it is going to be a voltage source to start with, but I'm going to use our foundation voltage source, so that's DC voltage source. So to start with, we're just recreating the behavior of an existing component so that we have a framework to build off to add more complexity. So if I make this 10 volts and run this, I'm going to get 10 volts out here. It's not rocket science. But I want to build my custom component, so I have a Simscape component right here. This lets me build custom Simscape components, put them in my model, but I don't have an SSC file to put in here yet because I haven't made one. Well, to start, because this is from the foundation library, this is not the right. I grabbed the wrong DC voltage source. I want this foundation one. Yes, they have multiple voltage sources. But this one has the source code available. So I'm going to click on that, and it's going to open the source code. And I want to take this. I'm not even going to look at it. I'm just going to take it, move it to my example battery, paste it, and change this to example battery, because that's my file name. I'm going to call this example battery, and I am going to delete all this. And say now this was copyrighted by MathWorks, so this is, you can't do this cut and paste and then sell your Simscape blocks, but they want you to do this to build your own blocks to use their products. So no worries with that. And I should be able to just save this as is, point here. So I haven't even really done anything other than rename the top level. And I have my 10 volt source. It's behaving the way I want. So let's actually stop and start getting into what the Simscape language is, so that we can start customizing this block to do what we actually want to do. Now the first thing we did was we went up here and we changed this. This is the model name. Component model name. So fairly simple. And then some text under here that describes it. So if I go back here and click on description, it'll show that, and then a source code link that'll take me back. Now, what is this? What is this right here? This foundation.electrical source. This is inheritance. So that means whatever text is in this file is essentially in this file. And that, from a development perspective, it might make sense why the Simscape developers do this, so that they can reuse a lot of code they're really familiar with. For me and the average person, we're not going to know what's in here. So instead of even trying to remember that, because like I can see here, this V, this equation, V equals V naught. V is nowhere else in this block. So what is V? What's it related to? So let's not deal with the complexity of inheritance. Let's just go here, open up this block, and I'm going to take the internal code from here, copy it. Do not modify this file. They let you modify the source files and break everything, so you'd have to reinstall. I don't know why they don't make it read-only, but that is the way it is. And I have just pasted that text in here, and I'm going to delete this inheritance. So that's the first thing I'm going to do, is I'm going to get rid of that inheritance, and I'm going to see if this still works. It still works, so I have successfully gotten rid of inheritance. Now it can be much easier to understand what's going on. So let's stop and actually look at what's going on. One thing you notice is we have parameters and equations and nodes and variables and branches and equations, and this is not a programming language. This is not something where things get executed in order. This is more of it's almost more of a markup language, similar to HTML, where you're defining things. So I need to have this parameters block. I need to have this equations block. It doesn't matter where they are. They're not executed in order. I'm just providing information to the Simscape engine. And you notice I even have two equation sections, and it just knows to combine them. So for my own sanity, I don't want to have multiple equation sections, because that's not intuitive. So I'm going to merge that and delete this. But Simscape would merge it behind the scenes for me. But it's good anytime I make a change, run it, make sure it still works. Okay, so let's talk about what these different sections actually do. The parameters section is where you specify user input parameters. And the comment is actually what is called a pragma, because this comment affects the user interface. What follows the comment value will show up in the user interface as the name prompted for. So if I click here and go to settings, this constant voltage setting is there. Well, I'm making a battery, so I'm going to say nominal voltage. And notice this says nominal voltage now. And the nodes, I can't actually see the node names right now. The nodes, which define your inputs for Simscape wires, these connect to nodes. And so these are electrical nodes, so it makes sense because it's a battery. We have a P, so we have a positive node and a negative node. And we're specifying their location, but we haven't specified their name. This part, right, so you actually specify their name here. So I'm going to add plus and minus. And I go over here, hit Control D. Plus and minus. Okay, much better. Now I can actually see the polarity of my component. Now variables. This is where we get into sort of fundamental systems of equations. Don't worry. You don't have to remember much. Just remember this. For the number of variables that I have, I need the same number of equations to solve for those variables. If I have more, I'm over-constrained, and if I have less, I'm under-constrained. So I need to have the right number of variables. And Simscape will straight out tell you when you compile if you have too many variables or equations. So I'm going to say V equals 5 volts right here. Save this. Run this. Number of equations exceeds number of variables. Just straight up tells me. So it's not like you have to keep track of it. It'll tell you, but it's good to know. And we're saying we have two states. We have the current through our variable, and we have the voltage across, sorry, not our variable, the current through our block and the voltage across our block. Now here's where something very specific to Simscape comes in. This branches section. Simscape assumes that all of your blocks have a through component and a cross component for its standard domain. So that's thermal domain, mechanical domain, electrical domain, magnetic domain. It gets more complicated when you get to fluids because you have a lot more states. But for these basic ones, you have a through variable and a cross variable. And for electrical, what goes through components? Current. What do you measure across components? Voltage. So for current, you have to define the branches of your component so that Simscape knows where the current is flowing from. So I am saying that current flows from the positive terminal to the negative terminal. I can flip it the other way. It'll just change the polarity of the reported current through this block. So it's important for bookkeeping and understanding where your voltages go. And typically, we define current as positive to negative. Then we have our equations. So now we have to label the equations that we have for the states. Now, take into account, Simscape can make equations from the branches because you've got KVL and KCL, so the current law and the voltage law. And so Simscape will use the current law to construct equations because it knows the current coming in must equal the current coming out. And then we have two equations here. So this actually gives us one equation, and this gives us three equations. Why does this work? This works because this equation and this equation can actually be simplified together. And Simscape does that behind the hood. So it's not that the number of equations I've written in my model have to equal the number of variables. It's that when Simscape optimizes things behind the scenes, it has to end up with the same number of variables to equations. And again, it will tell you if it doesn't have enough or if it has too many. So you don't have to worry too much about that. It'll give you that information. But we want to keep this voltage separately because this makes it really easy for us to define the voltage relationship of the component. And then this right now just lets us set a constant voltage to this parameter, but we want this to be a nonlinear mapping to state of charge eventually. So keeping this separately will make the readability of our model much easier. Instead of merging them, we're going to do them separately, and Simscape will optimize it behind the scenes at compile time, so it won't affect the runtime performance of our block at all. And it really doesn't have much of an effect on the compile time, little simplifications like that. So we now have this really basic block that we can start building off of. So we've accomplished the first goal. We have a constant voltage source, which we have gotten predominantly just by stealing and tweaking existing code. And we are going to continue that approach when we add resistance. So I want to add resistance to this block, and I could actually add equations. So I could add a parameter here for resistance, and I should actually do that. So I want terminal resistance, and I'm going to start it at 0, 2. And if you're curious about this method of syntax, this bracket number unit, this is how you specify a value when it has units attached to it. So this is just saying my value is 0.02 and its unit is ohms. So this is a value of 1 and its unit is volts. So in Simscape, you have units. The engine makes sure that your units match up, so it'll throw warnings if you try to push volts into amps or anything like that. So you have to get them right, but again, it'll tell you if you've gotten them wrong and where you've gotten them wrong. And it'll do conversions, like if you have something specified volts and something specified millivolts, it will handle that conversion internally. You don't have to worry about it. So it's a nice quality of life feature. But we want to add a resistance, and I don't actually want to write out equations. I could write the equations of a resistor. They're pretty simple. But I know that resistors already exist, so I just want to use an existing resistor block and bring that into this model, but I don't know the syntax for how to do that. And I'm not just saying that as if I'm you. I don't actually know the syntax off the top of my head. I do not use this language consistently enough to remember anything, and I don't need to. It's a simple enough language. You don't really need to remember anything other than some basic fundamentals. So I am going to do a really simple block right here. I'm going to do a voltage source, and I want to add a resistor. And you may wonder what I'm doing. I'm taking advantage of a feature that Simscape has. And I don't need this model to be realistic. I just need it to run. Okay, it runs. So I've got access to a feature called I can't spell, subsystem to SSC. And this subsystem takes a subsystem if it's pure Simscape and will actually create a Simscape block from it. So the command GCB gives whatever I've highlighted, so this untitled subsystem points to that. So I can do the subsystem to SSC block. Oh, there we go. That's all I needed. And it's going to create a subsystem from this block. So I'm going to be able to see how they programmatically connect the resistor up to a voltage source. And I'm going to do that. And I am going to take an extra step. I'm not just going to steal what they did. But over here it created this subsystem block. And what you can see, it's like, okay, created my component subsystem. All right, so we know what that means. That means we have a subsystem model. We have nodes, con1 and con2. Well, that makes sense because they're just the default con1, con2. And then we see this new section called components. Like, okay, so this lets us define components to add to our block programmatically. So we're adding that voltage source here, and we're adding that resistor. And what's really nice is that when you use this approach, it knows where the library is located. So when I can define my resistor, I could find this using the doc, but it'd be a little annoying. But here, it just gave it to me. And then also what its internal parameters and their names are, I can find that again, but it's a little hard. But instead, it just said you do R equals the resistance you want. So I want to take this section right here because I want to add a resistor to my block. So I'm going to go here. And again, it doesn't really matter where I add this. I'll go add the components at the bottom. And I don't need the voltage source, So I'll delete that, and I have this resistor. Now, I don't need this here. I already have a resistance, so I can take this terminal resistance, and I can add this right there. So that's the first thing. Now I've got a resistor. But if you notice, I also had this connections block, and so this connected everything up so that it works. Because I have to define what this resistor is connected to. So I'm going to steal that connections block, and here's where we're going to do things a little differently, because I don't have an external voltage source that's connected. I've built my own voltage source that essentially is defined right here, because I want programmatic control over how it behaves. So I don't have this voltage source, but I do have this resistor. So the way it works is you just point to two nodes. So voltage source.n, con1, resistor, voltage source.p. So I just need to use this connect terminology, and I need two of them for my resistor. So my resistor, how do I want this to work? I want my system to be like this. So here's plus, here's minus, so this is P, and this is N. And then I have my voltage here. So I need an internal node here to connect these up. That'll make my life the easiest. So I'm going to add an internal node to help me connect things. So this is the part that you wouldn't get just from looking at that. So I need it to be internal. So I'm going to set its external access equals none. And then here I'm just going to do P internal. Then this equals this. Same, I want an electrical node here. And so now I have this internal node. And now I want to rewire things. So first, my voltage is no longer P to N. I want there to be an internal voltage drop. So I want my voltage to be defined as P internal.V to N.V. So now my voltage source is defined here, and my resistor will dissipate energy. So now I need to connect my resistor from this internal node to this top level node. So I'm going to do, I've got resistor.P, so I want the positive of the resistor to be connected to just node P, like that. And then I want resistor.N, I want that connected to my internal node. So when it's a component that has multiple nodes, you do dot and then the node you're specifying. But inside here, I have direct access to my nodes P and N, so I can just reference them. So this should work. Maybe I got something wrong. I need to delete that. Let's see if we get an error. No errors. Will we have a voltage drop? So we don't have a voltage drop yet, so it doesn't look like I've quite got it working. I've got 10 volts and 0.02 ohms. So that part's working. So I probably messed something up in my connections. So let's go back and make sure I've defined everything correctly. Okay, so I readjusted where my voltage was. I do actually need to readjust where my current is, or it skips over that resistance. And so I want that, does that, now we get the voltage drop, yes. Now we have a terminal resistance, and now we want to go and make this a non-linear relationship. So we need to add some parameters to do this. I need to know so for SOC, I need to have energy storage. I'm going to add my amp hour rating. And then I need that nonlinear mapping. And so I'm just going to do a really basic. We'll take the mapping I created later. I started correctly, but then I forgot to give it units. So voltage data needs units. SOC is a unit list, so I don't need to add those brackets for this. So at 0 volts, I have 0 SOC, and at 10 volts, I have 1. So right now, I'm not doing a nonlinear mapping of SOC. So this is not how a battery behaves. This is just going to be a straight line. So this is going to be sort of like a weird, almost like a capacitor right now. Because the whole point of a battery is that you get this nice level voltage for the majority of your SOC, whereas a battery just is constantly drooping. Sorry, a capacitor is constantly drooping. So these are the parameters we're going to need, and we're going to need to put these into the equation. So this is where we actually start having to do some more serious Simscape programming. And so cutting and pasting is no longer going to save me. This is the portion where I need to think on my own. So we're going to do a few things. One, I'm going to want to be able to debug this, so I'm going to want to see what my SOC is, because I'm going to have to do that. So we're going to create an outputs, SOC out. And we're going to, this is a pragma, so it's going to be called S. Right now, because I'm just adding parameters and outputs, whoops, I'm curious if this will compile. No, it won't compile. Oh, I didn't give the units. There we go. So this, yeah, so SOC out isn't linked to anything right now. So it doesn't work. So just to do something very simple, I'm just going to say SOC out equals V. I guess I didn't mention, when you're doing equations, you do equals equals, because it's not saying V naught is assigned to V. It's saying there's a relationship where V and V naught are equal to each other. So the single equals is an assignment operator, and an equal equals is a relationship operator. So that will get relevant. Cannot use comma to specify port P, so I can't specify locations right now with what I'm doing. So I'll delete that. All right, now I've got this S that will be my SOC out. Right now it's just my voltage. So it's good to get things working a little bit piecemeal, so that you're not fixing everything all at once. Because it is hard, because it's not a procedural language, it is harder to debug. Because sometimes things just don't work. Yeah, so 10 is coming out of SOC, which is the voltage, so that's working. So I've got parameters now for amp hour, voltage, and SOC. I've got an output, but now I'm going to need to start doing the equations. So first, I need a sense of what my energy stored in my battery is. So I'm going to need a variable for that. So I'm going to do SOC. SOC equals, and so this is what's interesting, is SOC is unitless. It represents an amount of energy stored, but it doesn't, it's a value between 0 and 1, regardless of how much energy is stored. And so normally we might do energy stored here, but it's actually going to be easier, since everything's based off of SOC, if we use this SOC. So we are going to need to have a form of energy storage, but the variable is going to be here. So we're going to have to convert from energy to unitless down here. And so what is energy? Energy is essentially the integral of power flowing in. So this is where our first sort of calculus is coming in. And the way you want to do it in Simscape, you may be used to Simulink. In Simulink, you try to integrate and you try to avoid derivatives. Simscape's the opposite. You want to define derivatives. So I know that energy equals the integral of power, which means that E dot equals power. So this is the equation I want, not this equation. So I want to do SOC. How do I get its derivative? In Simscape, because this is a variable that I've defined, I can say dot dir. And now I can define its value. So my power is voltage times current. So this is really easy, but here's the problem. Let's actually see if it throws. And let's actually do this. SOC out. Let's see if this gives us an error. I think it will. Type mismatch for the equation. This is 1 over S on one hand, and the other is amps times volts. This is, so if I made SOC watts, I think this would work. Oh, because it's watts is power. So do I need to do watt seconds? There it works. So watt seconds. So if I make this, so watt seconds is energy. So I should have put in joules. I don't know why I didn't do that. So now I have energy. Now I'm not doing any limits. So this battery, because it's just outputting 10 volts no matter what, it's just giving off infinite negative energy. The reason I don't want to do this is because here's parameters, but I will eventually, let's make these available and show you what making them available does. Now I can set initial targets. So for SOC, I can set an initial target. And I would, instead of having to specify the exact amount of amp hours or the exact amount of energy in my battery, I would really like to just say, what's the SOC? I want to put like, oh, I just want to start at 0.8 SOC, instead of being like, okay, well, what's my nominal voltage? What's my amp hour rating? So what's energy? Like, I have to do math if I put an absolute value in here, whereas SOC is very easy to use. And that's why I want to do SOC as my state variable instead of power. But that means that instead of this very simple equation, I have to do a little bit of scaling inside, but it's going to make my life much easier the rest of the time. So let's go back and make this unitless. This isn't going to work. And I have to do, what I have to do is scale it by what is my energy storage capability. And that's it. We have that because I have my amp hour rating and I have my nominal voltage. So I can just go in here, and those have units. So this is marvelous because they already have units. So I can do V naught times, what is it? Just copy and paste instead of remember. See a theme in how I write code. So let's see. So I want SOC to start at 0.8 and set this priority to high. So Simscape will try to initialize it with this much power. Let's see if that actually works. Yeah, we're starting at 0.8 and now we're discharging. My SOC is going lower. So now I have a much more user-friendly form of power that's still related to real power and energy. So it's a much useful form of energy. So now I've got my SOC modeled. So now I'm tracking my energy correctly. And the final piece I have to do is SOC still doesn't affect anything else in my model, so I have to have instead of this constant voltage, I have to have SOC control what my voltage is. And so this uses so I've got this table lookup right here. And this is just a lookup table in Simscape. So now I can map voltage to SOC. So I'm going to put this in. And so this is actually, I just have to go here to do this. And so I need that table lookup. And so I'm looking at this right here. So x1d, x2d, x3d, x4d are the vectors. And then fd is the vector of the data I want, and then these are the data points that are being put in. So I want a voltage as my output. So voltage is what I want. So fd is my voltage vector. And this supports up to 4 dimensions, but I only have 1 dimension, and that's SOC. So SOC here is my first dimension, so I call that SOC data. So table lookup. So SOC data is my lookup data, and then my FD, my output data, so think of it as like function D, that is my voltage data. And then, this is all based on what is my actual SOC. So this is a little bit like standard programming, like I'm calling a table lookup, but I'm still doing this relational operator. So I'm just saying these relationships must be in place, and Simscape will handle it. And I think that might be all I need to do. Am I missing something? It's running. The SOC is going down is my voltage, and my voltage is going down. It's nonlinear. And if we make this like 1,000 seconds, how much does my... Yeah, so now my SOC is going down noticeably, and so my voltage is going down noticeably. But realistically, my voltage wouldn't go down this much on a real battery. So let's go steal the actual mapping that I did in this block. Whoops. No, that's the right one. And now I should get a more... Yeah, so 9.6 to 8.9 volts. It's a much lower drop. It looks the same slope because it auto-scaled. But if we were to... So let's start our SOC at 1. Run it for 2,000. And now we get that behavior we saw before. So now we have this realistic battery model. Well, simplified behavioral model, but it has certain aspects of it that are actually realistic now. And the final step is we want to make it look nice. And that is done using these annotations. So this is the final block I was working on, but we're working here. So we want to add annotations. And annotations let us control how everything looks. And I am just, for that, I usually go to the doc page for annotations, but I am going to steal from myself and just tell you what this code does, because it's more interesting than me Googling it one by one. So this first one, I take a node, and I just say, what side is it on? So node P is on the top, node N is on the bottom. And then I'm defining my output as being on the left. And then I've also made .svg of the battery. So I'm defining that icon. That lives right here. That's all this does. Save this. Control D. There we go. Now, it has probably incorrectly mapped the connections when that happened. Yeah, it did. So we'll just fix it all. There we go. And now we have a nice looking battery model. It's very simplistic, but it lets me create essentially any mapping from voltage to SOC that I want. Lets me see what my SOC is. I can initialize it based on SOC instead of having to calculate energy. And so the foundations of making this component will allow you to make most simple parts you could need to make in Simscape. There's some things with mode charts where if you want really complex behavior, and we'll go over that, and there's things like multi-domain models where we're going to do not just electrical, where there's additional Simscape language features that are relevant. But the most important thing that I taught you today, you may not realize it, but it is just this table lookup. Knowing how to say I'm going to specify my current and voltage like a normal component, but then I'm going to make the relationship this nonlinear mapping. This gives you the ability to make so many unique parts that are much more realistic than basic components you have. And so there's always certain scenarios where there's an effect that's happening to your component that's making its value change or its behavior change that just doesn't exist in existing modeling components. And oftentimes it can be represented with a lookup table very simply. Lets you give very accurate results, very fast results without having to do any complex math. Because you can do a chemistry-based model using PDEs to get this nonlinear relationship between voltage and SOC. But that's a component that requires thousands of states and probably months of development effort by experts. And if you have battery data, I can get this basic. We just did it in an hour. So there's times where you're going to need the chemistry-based models and the physics-based models. But this lookup table way of creating nonlinear mappings is one of the most powerful modeling techniques in letting you build accurate behavioral models to do what you need instead of puttering about with a lot of mathematics and research that you probably don't have the right background for, but you have data on what the system's actually doing, and so you can mimic it in your model and just move forward. So I really hope this is useful for you. The next the next video we'll do of this will be adding thermal effects, because SOC and terminal resistance are highly affected by temperature. So the next video will do multi-domain modeling. And then there's certain things like mode charts that are really powerful. I don't know how to map that to a battery yet, so I'll think of something to demonstrate mode charts for. And those will give you a really strong foundation in Simscape. But I think 90% of the time, if I'm doing something on Simscape, it's really just I want a nonlinear mapping that I can define. So I use this for building like custom saturation effects all of the time. That's a really common one in magnetics where I have to worry about and nonlinear thermal effects on systems. That's where I do it the most. I work in power electronics, so that's why I worry about that. We actually, in my side, we don't worry about the battery too much. We treat it like a constant source half the time. But anyway, I hope this was helpful for you. I'm gonna be a sellout. Please like and subscribe, just like everybody else says, and have a great day. Thank you.